Hello everyone, welcome again in Eng-Man YouTube channel. Today we will talk about pressure transient analysis in reservoir with single sealing fault. Okay, so it's a very important and interesting topic, and we will do the analysis using Saphire software. Before we jump into the software, we will talk a little bit about the basic concept. All right. Okay, here we have a well producing under radial flow regime. If we have radial flow regime, we will have log-log plot looking like this. The green line, of course, is a pressure line, and the red line is a pressure derivative line. All right. This section, this horizontal section, shows the radial flow. After the pressure transient reaches a sealing fault, a single sealing fault, we will have half radial flow or hemi-radial flow. And we will see a trend like this. All right, so our pressure derivative will increase like this one, and then will stabilize again. So this stabilized region here indicates our half radial flow. So that's the basic concept if you flow under half radial flow regime, which occur if you have a sealing fault. In this case, single sealing fault. All right. Now, if we plot and we obtain the Horner plot, we will have trend like this. Okay, we will have two radial flow. The first radial flow can be taken from this section. It shows our IARF, which is infinite acting radial flow. This is the first radial flow. Okay. And after that, we will have half radial flow with twice the slope here. All right. And this second radial flow will be used to obtain our P star. Okay, so this is the Horner plot. And this is, of course, the log-log plot. Again, our radial flow is located here in the first stabilized section. And the next stabilized section is our half radial flow. From the radial flow, from the first stabilized radial flow, we can obtain our permeability and the skin. And we can obtain or calculate or estimate the distance to fault by considering this section. All right, where the deviation first occur. And this is the sensitivity to boundary distance. As you can see here, the closer the fault is from our producer, then the boundary response will be felt sooner, like this one. If the boundary is very close to the well, like this one, if we have the fault located just 100 feet from our well, then the infinite acting radial flow may not develop before the fault is detected. Okay, so for very nearby boundaries, the pressure response could look like a homogeneous infinite response with an apparent permeability thickness equal to the half of the true permeability thickness. Okay, so like this one, we think that this is an infinite homogeneous reservoir, and we may take this as our permeability thickness. But actually that's wrong, because the true radial flow is masked by the fault response. Okay, so this is actually not the true radial flow. And of course, the permeability thickness obtained by analyzing this section will be wrong. It's just an apparent permeability thickness, all right, which is half of the true permeability thickness. If we have L equals to 1000 feet, the radial flow, the first radial flow can be analyzed. It's quite clear, and then it will deviate, indicating fault, and then we will have our second stabilized radial flow. And also for L equals to 3000 and 10,000 feet. All right, so that's the point. That's the basic concept for pressure transient analysis in reservoir with single fault or from a well located nearby a single fault. Okay, so I hope the explanation is clear and we will jump into the Saphire software. All right, so this is the Kappa workstation. We press this one, blank. Okay, next. Name analysis one. Okay, well radius, default, pay zone also, 30 feet, rock compressibility, the same as default, porosity, 20%. Next, reference oil, okay. Formation volume factor 1, viscosity 1, total compressibility 3 times 10 to the power of -6, okay. All right. Step 5, first analysis, vertical anisotropy, okay. Next, wellbore storage constant, well model finite radius, reservoir model homogeneous, boundary model first, okay. If we select infinite, later on, we will change to single fold, create. All right. We need to load our flow rate and pressure data. So we click this one, load flow rate. All right. Now from here, we will first look at the spreadsheet where we will have our data. So we go to our spreadsheet. This is our flow rate data. So we will have two periods, flowing periods for 3 days or 72 hours, where our well will produce at flow rate of 1000 stock tank barrel per day. And after that, we will shut in the well for 7 days or 168 hours. So the flow rate will be 0. Quite easy for the flow rate data. And what about the pressure data? This is our pressure data. First, elapsed time in hour, and then pressure in PSIA, like this one. And after we plot the pressure data, we will get this plot. Of course, this will be our flowing period. Okay. Followed by shut-in or build-up period. As you can see, after several hours or several days of build-up, we still cannot reach our initial pressure. The initial pressure is 5,000 and the last build-up pressure is, we go down this value. Okay, and this is the line indicating our initial pressure, and you can see there is a depletion, all right, where our initial pressure is higher than the last built-up pressure. Okay, so far so good. We have prepared our pressure data as well as our flow rate data. So first, we need to copy this flow rate data and go back and paste on the software. All right. After copying the data, we can just click this one. All right. Copy from clipboard, and we will have our flow rate data here in preview of clipboard window. And then next. Okay. You can see the time format is duration. And the other thing, okay. Type decimal time in hour, oil rate in stock tank barrel per day, 1000 stock tank barrel per day, 72 hours. All right. The flowing period. Okay, load. All right. It's quite good. Perfect. This is our flowing period, 1000 stock tank barrel per day, followed by build-up period with 0 flow rate. And then we do the same thing with pressure. I will just copy my pressure data and then copy from clipboard like this one. Okay, click next. All right. So here, the time format is points. So be careful there. Okay, in points, decimal time, hour, pressure, PSIA. All right. The initial pressure, 5,000. And this is our pressure data. Load. Okay, skip new data, apply to all. Okay, perfect. All right, so we have loaded our pressure data as well as our flow rate data. All right, from here, we click extract pressure drop. All right, you can see this is our log plot. You can click this one. All right, we will concentrate on the build up period. Close. Okay. All right, interesting. So we will have three plots. The first one is our log plot, and then the Semilog plot, and of course our history plot. The results will be shown here in standard oil analysis. Okay, first, we will start by discussing about the Semilog plot. Okay, maximize, right click, results in plot. Okay, and then in Semilog plot, we can do analysis with single line. So how to do that? Right click, single line, and you can just click and block the periods where you think you can take or you can obtain the radial flow. In my case, I think the radial flow will be located here. So I'm just going to click and then drag here to create straight line like this one. All right, beautiful. Okay, so you can see this might be our first radial flow, the infinite acting radial flow, and this might be our second radial flow or half radial flow with twice the slope. All right, so the slope here will be twice the slope here. And the results is shown here. With Semilog plot analysis, we can get permeability of around 85 millidarcies. We can also calculate the skin, and we can get the P star from Semilog analysis. All right. And if you minimize the plot, we will create this one, this green line, which is taken from our Semilog plot. So the period highlighted here is actually the period highlighted here. And of course, from the log plot, we can say that our radial flow will be located here. So it's quite good. All right. The straight line we take in this section is actually a good location where we can take our infinite acting radial flow. All right. This is actually the good or the proper location from which we can obtain our permeability information. So we can say that our permeability is close to 85 millidarcies. Of course, we will prefer permeability information obtained from log plot rather than Semilog plot. But it's a good start. We can say that our permeability is close to 85. Okay, so far so good. We can minimize. All right. Right click, uncheck the results in plot. Okay. Right click, results in plot. We can concentrate on C, wellbore storage coefficient, permeability, and we can also add tools, single fold. But let's do that later after we obtain our permeability. So first, wellbore storage coefficient by dragging this dashed line to the left or to the right. Of course, we'll locate our dashed line here. Okay. So our wellbore storage is of this value. And of course, we will deal with our permeability. We will obtain our permeability by dragging this dashed line up and down. Of course, we should locate our dashed line at this first stabilization period. This should be our first radial flow. All right. Yeah, you can see the permeability is 91, quite close to the permeability information obtained from the Semilog plot analysis. Results in plot 85, right? And our permeability from log-log plot analysis is 91. It's quite good, right? So we have completed our analysis for wellbore storage coefficient and permeability. All right. Then we add the tools, single fault. All right. So this is the tools, the analytical tools for single fault. Okay. We will add a new variable L, which indicate our distance to boundary. In this case, a fault. Okay, so we can first uncheck the results in plot, and we can move the tool to the left or to the right like this one. Okay, we should match the tool with our pressure derivative. Quite easy, right? Okay, maybe it's not that match, so maybe we can lower down our permeability, this one, to make it quite perfect. And at this point, we can show the results, right? You can see if we drag it to the left or to the right, you can see the L will change. Okay, we can locate our tool here to obtain a quite good match, or maybe at this point. So our fault is located around 561 feet from our well. So that's very good, right? Using log-log plot, right? Using this analysis, we can obtain our wellbore storage, permeability, as well as our distance to boundary or distance to the ceiling fault. Okay, so we can minimize. The results is shown in standard oil analysis window. Okay, the initial pressure 5,000, permeability thickness, permeability around 91 millidarcies, wellbore storage, as well as our distance to fault. So it's very interesting. Of course, we haven't done yet. At this point, we can go to analytical. All right. Using this analytical, we will generate the analytical model. So we can click this one, reset from diagnostic, to make sure that our starting point is the results taken from the previous analysis using log-log plot analysis and Semilog plot analysis. Okay, like this one, initial pressure, permeability, right? Thickness, porosity, and distance. Okay, so for wellbore storage model, of course, constant. It's a vertical well model. Reservoir model homogeneous, and the boundary model using ceiling fault. Okay, so we can generate. All right. The first one will be quite like this one, not very good match, but it's okay because we will refine the analysis or refine the matching. So no problem there. The same thing with this Semilog plot and also for this one, history plot. Maybe we can, yeah, we can move this one like this, but we still cannot obtain the good match. So we need to do improvement. All right, minimize. Now we can go to improve, tested well, log-log. So the matching will be based on the log-log plot rather than the history plot. All right, we can do the first run. Let's see. All right, with only one run, we can obtain a perfect match. A perfect match for the log-log plot, Semilog plot, and of course the history plot. Let's check them one by one. Okay. At this point, we can uncheck the show tools and uncheck the show model if you want. But let's maintain the model. Right. You can see, right? A perfect match. If we maximize or zoom in, very good. The matching is very good, right? Okay. Reset. All right. Very good match also for Semilog plot. Results in plot to see the results from previous analysis. Very good match, right? Maximize or zoom in. All right. Click this one again, reset, and also the perfect match for history plot. Zoom in. Yeah, very interesting. Okay. All right, so we have completed the analysis for semi-log plot, log-log plot, and history plot. We obtain a perfect match. And now let's see if we do sensitivity. We go to sensitivity. Of course, we are interested in doing the sensitivity for distance. Oh, first, we need to check the results. So actually the permeability is around 100 millidarcies. All right. This will be the best results. So the permeability is around 100 millidarcies. Initial pressure of 5,000. Skin of -5. L is 500 feet. Distance to fault is 500 feet. All right. So using this L, we will do sensitivity. Go to sensitivity, check the distance, click this one. Let's see just 3 scenarios, 250, 500, 1000. Okay, to obtain our sensitivity. All right, right click, legend. Yeah, you can see in the first plot, the blue, the light blue plot, we have a very short radial flow or stabilization period. All right. If we have the fault located just 250 feet from our well, and of course, in this case, if we analyze or calculate our permeability using this stabilization, we will obtain a false result because it's just an apparent permeability thickness or apparent permeability. It's not the true stabilization period. It's just an apparent stabilization period because the true stabilization period is masked by the response from the fault. And then we have our second scenario where we have our fault located 500, the same with our model. And for L equals to 1000 feet, we will have longer stabilization and then the deviation to the second stabilization. All right, let's try again. Sensitivity, open. What about if we have 50 and 5000? Okay. Wow, that's very interesting. If we have a very close boundary, we can have this situation. We will lose our true stabilization and we will lose our true permeability thickness. Okay. And if we have a fault located very far from our well, in this case, located 5,000 feet from our well, then maybe we cannot detect our fault if we flow our well in just 7 days build up. Okay, so it's quite clear. So we can recap. In this video, we have learned many things. We have done the pressure transient analysis for a well located close to a ceiling fault. We have completed the matching. We obtained a perfect match for log-log plot, semi-log plot, and history plot. We do the analysis using Semilog plot. Here we can get a guess permeability. We can cross-check the number or the permeability from Semilog plot with our log plot. And then later on, we will refine the analysis using analytical and improvement. All right. Also, we have used the tools from Saphire, the tools to determine the wellbore storage coefficient, the permeability, as well as our distance to fault. So that's all. I hope you enjoyed the video. I hope the video is interesting. So please don't forget to press like, subscribe, and share to your friends. And thank you so much for watching. See you again in the next Saphire videos. Thank you.